In this video, we are going to explore the periodic table in more detail, and we are going to use the 20 element cards that you were asked to make in order to do so. So to start off with, the periodic table was an invention of a man by the name of Dmitry Mendeleev. He was a Russian chemist, and in his studies of chemistry, he noted that there was a pattern amongst the elements that he was aware of and that he had studied, and he started to put these elements according to these characteristics in a structure which today we call the periodic table of elements. The amazing thing about Dmitry Mendeleev is that at the time he had very few elements that he actually knew about, and yet he was still able to see the structure. So in essence, the periodic table of elements is just that. It's a table or structure of the elements that we know. It's not a mixture of elements, it's not compounds, it's purely a table of elements, and we'll learn more about elements later on in the grade 8 syllabus. So for now we're going to look at the basic structure, and the periodic table of elements is structured in columns which are vertical, and these vertical columns are called groups. And you're going to see a little later on in this video that the elements are arranged in groups according to a very specific, unique characteristic that makes them all common. So we are looking in the first 20 elements, we're looking at the 8 groups, and note that we are using a different number system in order to identify them. So we're using the Roman numeral system, so this I is in actual fact 1, 2, 3, this I and V is 4, this V is 5, V and I is 6, 7, and 8. So we're going to work with the 8 groups. If one goes further and one works with what we call the transition metals, then we can switch to an American system of using many more group numbers, but then we don't use Roman numerals, we use the normal numbering system that we use on a day-to-day basis. So we're working with 8 columns, and we are working with also rows. So the rows are what are referred to as periods, and like with the groups, they have a very specific, very unique characteristic for each element, each atom that appears in a particular period. So we use P for period, and we use normal numerals, P1, P2, P3, and P4. So now we're going to look at each of the groups and each of the periods individually. The first group is also known as the alkali metals, and we'll see later on why. But for the time being, if we look at each of the Bohr model diagrams for each of the atoms of the elements in the first group, you will note that each atom has only one valence electron in each of the atoms. So we see here, and remember the valence electron or the valence electrons are the electrons that occur in the outermost energy level of an atom. So in each of these atoms, in potassium, there is only one electron in the outer energy level. In sodium, there's only one electron in the outer energy level. And in lithium and hydrogen, there's only one electron in the outer energy level. Now, you might be saying, but why is hydrogen, which is not a metal, in the alkali metal group? And the reason it is there is not because it's a metal, but because it has the same valence electron structure. And the amount of valence electrons, I'm going to use VE for valence electrons, basically determines certain chemical characteristics. And in the case of group 1, what we find is that all group 1 elements are actually very reactive, chemically speaking. And in the case of the lithium, sodium, potassium, and the other metals in group 1, when they react with water, they produce an alkali, which is a base. So when a group 1 metal or group 1 element reacts with water and you add it to water, then what it does is it produces an alkali plus hydrogen gas. There is just one exception, and that is obviously hydrogen gas as an element. So from this example, one can see that there's a reason why the lithium and the sodium and the potassium are in group 1. They're all metals. They all have one electron in the outer energy level in the valence shell. And in the case of hydrogen, it's got a similar valence electron structure to the other atoms in group 1. So group 2 is referred to as the alkali earth metals. And the reason for that is that these substances are found in quite great quantities in the Earth's crust. And like group 1, when these elements react with water, they do so in quite a reactive way, but they're not as reactive as group 1 elements. And that there's a reason for that, which we will look at later on in your chemistry on high school level. And they too produce alkalis or bases when they react with water. So now when we look at the amount of valence electrons, we see that each of the atoms in this group has 2 valence electrons. Even though they are in different periods, they have the same amount of electrons in the outermost energy level. And it's this that gives them their specific chemical properties. In particular, it impacts on their reactivity when they react with other substances. So we are now going to move further through the groups 3 to 8, but we're going to do so now quickly, because by now I'm hoping that you're starting to see that there's a pattern between the group number and the number of valence electrons. We don't give group 3 a specific name, but in group 3, all the atoms in group 3 have got, yes, you guessed it, 3 electrons, as you should have been able to pick up when you actually drew your cards for each of the elements atoms in the first 20 elements. So we can see 3 and 3. Group 4 has atoms that have 4 valence electrons in the outermost energy level. Group 5 has atoms that have got 5 valence electrons in each of the atoms in group 5. As we can see the amount of core electrons varies because as you'll see just now, these atoms are in different periods. So now we move on to group 6. Group 6 elements do have a name. They are referred to as the chalcogons. And in group 6, we find oxygen, which is so necessary for so many processes, like, for instance, combustion, which produces energy from fuels, as well as metabolic processes where we gain energy from our food in our bodies. we know that without oxygen we won't be able to live because we need to breathe oxygen in. But if we look at oxygen, we see that oxygen is sitting in group 6, and it has 1, 2, 3, 4, 5, 6 valence electrons. We expect that. And sulfur has also got 6 valence electrons. Therefore, both of these elements sit in the chalcogen group, which is group 6. Group 7 are well known, and they are referred to as the halogens. Now, they are extremely reactive, but they also happen to be very, very poisonous. So they have 7 valence electrons in their outer energy levels, and that makes them very, very reactive, as you will learn about in grade 10. And they are used in some well-known poisons. So for instance, chlorine gas was used during the First World War as a poisonous gas in the trench warfare. Fluorine is actually used to fluorinate our water, as is chlorine, in other words, to kill germs. So they don't only have purposes or uses that are negative. They are also used to clean things, but they are highly, highly, highly reactive because they have 7 valence electrons in their outer energy level. Now, right next to group 7 are the group 8 elements that are referred to as the noble gases or the inert gases. And in stark contrast to their group 7 neighbors, which are elements that are highly reactive and highly poisonous, we find that noble gases are non-reactive. And the reason for that is that they have full outer energy levels. So if we look carefully here, we see that neon has got 8 valence electrons and argon has got 8 valence electrons, and so their energy levels are full, their outer energy levels. So these atoms have got 8 valence electrons. But you might say, but well, wait a minute, you're hiding something. You're hiding the fact that in this group there is helium, which has only got 2 valence electrons. So how can it be that helium sits in group 8 and yet it hasn't got 8 valence electrons, it's only got 2? And the reason for that is, if you look carefully, the outer valence shell is full. And that makes these atoms non-reactive, chemically speaking. So in chemistry, we at times refer to rules, and I just want you to be aware of the fact that the rules often have exceptions. And so here is an exception to the rule, that the rule that I'm referring to is the rule that the group number is equal to the number of valence electrons in the atoms of the elements in that group. Here is an exception to the rule. While helium's outer energy level is full, and that's why it's in the inert gases, inert meaning non-reactive, it doesn't have 2 valence electrons. So we must always be aware of the fact that when we learn rules, we must also learn the exception to the rules. So now let's move on to the periods in the periodic table. So in period 1, we can see that the hydrogen and helium don't have the same valence electrons, but what they both do have is only 1 energy level. So, and this is why hydrogen and helium both appear in period 1 in this row, because the energy level in each of the atoms is only the first energy level. If we now look at period 2, and we look carefully at period 2, and I would like you to also refer to your cards and check that your cards correspond to the cards that I have, that you have the right Bohr model diagrams for each of the first 20 elements. If you see here, you can see that in period 2 each of the atoms has 2 energy levels, and so this holds true for all of them, all the way up to neon. So all these elements have atoms with only 2 energy levels, and while their number of valence electrons varies, the number of energy levels is constant. So let's now move to period number 3. In period number 3, we find that the atoms here each have 3 energy levels: energy level 1, energy level 2, energy level 3, and this is true for all of these atoms in this period. They have only 3 energy levels: 1, 2, 3. And so we can see now that the period is an indicator of the number of energy levels in the particular atom. And so lastly, in period number 4, we see that the elements that we have in period number 4 have 1, 2, 3, 4 energy levels. And so now we can make a set of rules, very basic rules, that can help us in grade 8 to understand how many energy levels there are in a particular atom and how many valence electrons there are. So the rules are: rule number 1, the group number equals the number of valence electrons in the atoms of the elements in that group, except for helium, which sits in group 8, but the number of valence electrons is 2. Rule number 2 is that the period number is an indicator of the number of energy levels in the atoms of the elements in that group. So let's see how useful these rules are. So let's assume we have an atom in group 4 and period 3, and we were asked to sketch the Bohr diagram. So we could say, well, okay, we look at the amount of energy levels. So we've got the nucleus here. There's the nucleus, and the nucleus is positive. And we have how many energy levels? Well, we see that period 3 tells us that we have 3 energy levels. So it's going to be energy level 1, energy level 2, energy level 3. So we know that we've got 3 energy levels. The fact that it's in group 4 tells us that it has 4 valence electrons. So in the outer energy level, there are 4 valence electrons. And the 2 inner energy levels, the core energy levels, or the core shells, have very specific amounts of electrons that can fill them. So energy level 1, we know, can only take a maximum of 2 electrons. Energy level 2 can take 8. 1, 2, 3, 4, 5, 6, 7, and 8. So this particular atom has a total of 2 plus 8 is 10, 11, 12, 13, 14 electrons. So there are 14 electrons. And because it's an atom, we know that there are 14 protons. And because now we know that it has 14 electrons, we can now go and find out on the periodic table which element this atom represents. And it happens to be silicon, which has an atomic number of 14, and we'd have to go and look on the periodic table, and silicon has a mass number of 28, which means that it would then have to have 14 neutrons, so that 14 neutrons plus 14 protons gives us 28 nucleons, and hence the reason for the mass number of 28. And so this is a very useful method for us to quickly pick up on the number of energy levels and the number of valence electrons in the outermost energy level, which enables us to identify certain chemical properties which we will need to work with later on in our chemistry on high school level. In the next video, in this video series, we are going to look at ions, that is charged atoms, and we are going to look at patterns for ions on the periodic table.